I am so excited today because I finally get to take a break from solving LeetCode problems and do something that I find actually more interesting, system design. Yes, we're finally getting back into it, and today I actually have a very special announcement. This here that I've been working on, this is a little write-up with some images and a lot more, is actually a part of my new newsletter, which is completely free. You can sign up for it on neetcode.io/newsletter. Link will be below. Covers coding interview prep, system design, career advice, tech news, and a lot more. If you sign up, you'll get access to a 500-page system design PDF, and pretty soon I will be creating a PDF with a bunch of algorithm animations and lessons and things like that. It's going to be completely free, and if you're a subscriber to the newsletter, you will get that. So the quick agenda for today, I know this is light theme, don't worry. I'm not just going to be going through this and reading it to you. That would be too boring. We're going to be doing something even more interesting. We're going to cover all of this, which is how Notion is using SQLite for caching. If you know me, you know my style is very hands-on. I like to draw. That's what we're going to do. We're going to go through kind of the background, talk a little bit about what SQLite is, how it's used in the browser, how Notion uses it, a little bit about web workers. We're going to be doing some coding for that, and a few more diagrams, and we're really going to be digging into the details. If you're the type of person who just likes to hear a bunch of keywords, sharding, caching, all that stuff, that's cool, but to me, that's boring. I want to know the details, what's actually going on. That's what I'm going to go over. So the first thing I want to do is just go over a little bit of the background about Notion and do a little bit of dev tooling. So this is the Notion UI. It's a website. It's kind of a productivity tool, also very similar to Google. Google Docs in that like there's a bunch of documents. So now let's take a look at the dev tools. I'm specifically going to go over here to the application tab, and then I'm going to go to storage here. You can see right now Notion is using 7 megabytes. I mean, I just created this brand new account. So 7 megabytes isn't a ton. It's probably a bunch of like metadata and a few of these pages that are created by default. And so watch what happens though. When I take all this text here and I just copy and paste it into the same document a bunch, watch what happens. Do you notice the storage on the right side? It seems to be increasing. And so now when we refresh, the data that we stored is persisted. All of this data is cached locally to our file system. This is not something that's built out of the box. This is something that has to be coded manually. And that's exactly what Notion did. That's what we're going to be talking about. Now, we'll be talking about this more in depth, but I want to quickly say Notion is using SQLite for caching locally to the file system. Now, an alternative could have been local storage, right? It's definitely using local storage for certain things here, you can see. But why would it be a bad idea to cache like the document data itself? Well, let me show you. This is my personal Notion account, and you can see that I'm not even like a big Notion user, but it's using 4,000 megabytes. That's 4 gigabytes. Storing all of that within local storage is not really feasible. That's not what local storage is for. And not only that, but writing to local storage is not as efficient as doing it via SQLite, and we'll talk about exactly why. So first, Notion's objective here was to implement caching in the browser. This would result in faster page loads as well as navigating between pages. Why exactly is that? Well, the alternative to reading from the local cache, which by the way, this is a disk-based cache. Cache is a very loose word, but it's generally faster to read from disk than it is to make a network request, which is what the case would be if we were going and reading from Notion's backend for like every single page. And so Notion was successful in doing this. They did reduce latency by, I think, about 20%. And here's how they did it. Well, I think it's worth covering what exactly SQLite is, because it's definitely different than a traditional relational database like Postgres or MySQL, and even NoSQL databases like MongoDB. The traditional setup is typically a client-server setup where you have a server that's running some application code, for example, Python or something else. And then that code will read and write from a database that's typically hosted on a separate server nowadays, but you technically could have that database running on the same server, and then those two processes, those separate processes, could still communicate via some protocol. And remember that a process is an operating system unit. Your operating system is managing that process. Every process has its own memory, and it could be made up of multiple threads. Now, SQLite is actually very different. Kind of like the name implies, it's light. It does not require a separate server. Not only that, you generally can't run it on a separate server. It runs alongside your application code via a single process, one process for the database and the application code. Now, SQLite still has actually a lot of support for database indexes like SQL support, queries, tables, a lot of functionality, probably not as much as Postgres. Like, it does not have the feature parity of Postgres for sure, but it has a lot of the functionality, but it has a lot of limitations. As you can kind of tell, I mean, if the code and the database are running on the same process, the obvious limitation is that the data can only be stored locally. So if this code is running on a user's machine, maybe their phone, their browser, well, it's going to store the data in the same place. It's not going to persist that data to Notion's servers. And of course, in Notion's case, this is all happening within the browser. You pretty much just install SQLite as a dependency, as if it's a library, like a Node.js dependency, a Python dependency, etc. In terms of the use cases of SQLite, one, we kind of mentioned the browser. So it's definitely used for web development, but since that data is stored locally, it's generally used as a cache because, of course, if the user like clears their cache, clears like the data in their browser, all that's going to be lost. Or maybe if they switch to a different machine, all their data is going to be lost. And that's perfectly fine if that same data is also stored within Notion's servers. Now, a couple other use cases you can read a bit more about in the newsletter itself is embedded systems. also desktop and mobile applications. Now, we know that generally in the browser, the code that you can run is very limited, and that's intentional, like for security reasons. Generally, you can run JavaScript, and even that will have limitations on what it can do to like the operating system. Yes, it can write data to disk, but it's limited in how it can do that and the APIs that it can use to do that. You wouldn't want somebody's JavaScript code to write a bunch of bugs and malware and things like that to your computer. But browsers also have the ability to take some code that's actually things like C, C++, Java, languages that are not JavaScript. And then this can be compiled on a server, like this, a server that's separate from the web browser. It can be compiled into a language called WebAssembly, or this for short. And then a browser can actually run this code. So in a sense, browsers actually can run these sorts of languages. And the reason that this is important is because that's exactly why they can use something like SQLite within the browser. They're using a WebAssembly version of SQLite. And we know that it has to be able to write to the file system, and it's going to be able to do that, something called the file system API, specifically the Origin private file system. You can read more about these in the newsletter. This itself is not enough. Remember, we talked about local storage. How does that compare to SQLite? Well, first of all, local storage is very limited in the data it can store. For example, megabytes of data. But as you saw in my case, I have 4 gigabytes stored in Notions. Local storage is not going to be enough for that. So SQLite will allow us to store additional data than local storage. That's one. That alone, by the way, is a big enough reason to use SQLite. But if that's not enough to convince you, let me tell you something else. We know that in the browser, JavaScript is generally single-threaded. There's the main thread. And so if we are writing to disk via local storage API, if we're writing to local storage, that actually is not asynchronous. It's a blocking IO call. So it's not asynchronous, it's blocking, meaning our main thread is going to wait for that to complete before going back to the JavaScript, like the main code that we were writing and executing. And all of this has to happen within a single thread. But the benefit of SQLite is we can actually run this in a separate thread. And of course, that would be great for performance reasons. It'll be faster to do this, and it will be asynchronous. All of this is accomplished with something that I'm going to go over now called web workers. So I'm going to take a couple seconds to draw this a little bit visually, and then we're actually going to get into the code. I really want you to understand what web workers are doing. Imagine you have a main thread, like the JavaScript main thread. We can also spin up a new web worker, which will actually run JavaScript code within a separate thread. And within that web worker, you can imagine what we're going to do. That's where we're going to run the SQLite operations. We can use this to write to our file system, and this can probably be done in parallel as the main thread is running. The reason it's important to do this is because this is very computationally intensive. It's going to possibly be reading lots of data and writing lots of data. Doing all of this in a separate thread is very important. You might think, well, couldn't you have done the same thing with local storage? Well, I mean, even if it weren't for the data limitations, I don't believe local storage can actually use the web worker API, at least not directly. I think it might be able to send data to the main thread if it needed to, and then the main thread would be able to write to local storage, but obviously then there would be no benefit of doing this in the first place. So now let me actually show you a bit about how you can actually code up a web worker. It's not as complicated as you think, and when you actually look at the code, that's when you'll be able to remember this stuff in the future. So I have a very small example I want to show you. I'm going to go through this relatively quickly. So I have my index.html. I just have one script linked to this. That's my main.js. And within here, I'm going to copy and paste a little bit of code. So here we are creating a new web worker. We're using the web worker API, and we're passing in the path of a file. Notice how that's the same as the file up above. Remember, these are separate threads. If you remember operating systems and parallel programming, you know that threads have to communicate with each other. They don't necessarily share the same memory and same variables and all that. So communication is kind of done via this API. You can see worker.postMessage. We're sending this data. It's in the form of a string, but it didn't necessarily have to be that. Look, you can see that the type would be any. We could have passed in an object or more data if we wanted to. And this is how we send data to the worker. We can also listen for messages and then execute some callback. For example, in this case, worker.onMessage. Whenever we receive a message, just take the data of that message and just console.log it. Pretty simple, right? Now, in terms of the worker itself, it's even more simple. All it does is listen for data from the main thread. Whenever it receives that, it'll take the data and then just console.log it. This is the data we received from within the worker. And then we're going to send data back to the main thread just with post message. So you can see the self keyword here is kind of the distinction between that and here. Here we're using worker.postMessage on message. Here we're doing self.onMessage post message. By the way, if you're a beginner, a friendly tip would be don't try to memorize all this. I don't memorize it. It's not really worth memorizing. You can just Google it or nowadays ChatGPT it. At least now you know that this is possible. You have this as a part of your toolkit. At least try to understand the high level. Hopefully this code looks pretty reasonable to you. An even better tip would be to code all of this yourself. Try it out, run it locally, which is exactly what I'm going to do now. I'm actually going to run this server now and show you what it's going to be doing. What would you expect it to do? Well, it's going to execute this script and execute this script. So in theory, it should console.log a few things. So let's run the server. I'm going to do that in VS Code using the live server extension. I opened up the page on localhost 5500. Let's take a look at the console tab. And here you can see that this line received in the worker, hello from main script. You can see that this is logged from within the worker. So this line executed first because main.js was the one that initiated all of this. You can see within main.js, we sent the message to the worker, this message, and then the worker logs that message. Then the worker sends data back to the main thread, and then we log what we received from them. That's why the second line is hello from worker. That's the data that the worker sent. Pretty simple, but this is what Notion used to implement caching efficiently. Now, imagine that you're Notion. You spent all this time trying to improve performance, and you actually did, so it's like about 20% better for most users. But what if for a small percentage of users, let's say like 5% of users, people that are on really old devices, like maybe a really old Android phone, and they're running like the Notion Android app, or even using it within their browser or something. Imagine that for some of those users, it's actually slower to read from disk than it is to just make a network request to Notion's backend. Maybe they have a really, really good, efficient backend, and you have a really, really bad phone, bad hardware, really slow file system, maybe a crappy CPU, single threaded. So the web worker doesn't even do anything, at least in terms of like performance improvements. You tell me, in this scenario, what would you do? It only applies to a small percentage of users. Well, I guess I kind of spoiled it for you by having the correct answer right in front of you. You would race the two requests. So at least that's what Notion did. And it turned out to be a pretty smart solution, because think about it. The Notion Android app starts. You make two requests at the same time. You read from the file system and you call Notion's backend. Whichever one of these requests finishes first is going to be the one that you get the data from. So for example, like for 5% of people, this one will be faster, but for 95% of people, the cache, the local file system will be faster. The fact that we have multiple requests going, maybe the cache is actually out of date and the backend has newer, fresher data. I think that could also be a potential benefit. Maybe this architecture is used for more than just the Android app. Pretty smart, pretty clever, and a very, very simple, elegant solution, in my opinion. Now, latency is bad, but you want to know what's even worse? Data corruption. That's the more serious issue that Notion was actually encountering. Imagine that a user has Notion open in multiple tabs. They just opened like 3 different tabs. Each of those tabs is potentially going to fetch fresh data from the server and maybe cache it to the local file system via the web worker. And you might have multiple web workers doing that concurrently at the same time. Well, can you believe that this actually resulted in data corruption? And the fix is relatively simple, so I'll go over that quickly. We could have a shared web worker, which is implemented slightly differently in terms of code than the web worker code that I showed you, but it is like pretty similar. And what happened is we load, let's say, multiple browser tabs. Each of them needs to write data to the SQLite cache. And instead of each of them directly sending it to its own web worker, we do something different. We send all of them to the shared web worker, and the shared web worker will direct it to a single web worker, which is going to be the active tab. And that is going to write to the SQLite cache. And this way we guarantee only one process is doing this at a time. And it makes sense because only one tab can generally be active at a time. I mean, you might have multiple windows open on multiple monitors even, but even in that case, isn't it true that you can only select one tab at a time? You can only be like truly active in one tab at a time. This basically helped to mitigate the data corruption. But do you smell that? I heard that SQLite is actually ACID compliant. It is. And more specifically, we focus on the I. Remember that it stands for isolation. If you don't know this, by the way, I cover all of this in my System Design for Beginners course. I just don't have time in this video to explain every little thing. But isolation in general should mean that multiple concurrent writes will not interfere with each other, and they definitely shouldn't result in data corruption. So it seems like there's a contradiction. Why is that? Well, it wasn't SQLite's fault, actually. According to Notion, it was actually a result of the browser's OPFS API, which is the one that's actually responsible for the read and writes. That was the part that wasn't handling the concurrency. That was resulting in concurrency issues and data corruption. And this is exactly the kind of detail I think a lot of people gloss over, but I thought it was worth mentioning. I think I'm going to go ahead and leave things there, but if you prefer the full written version, definitely check out the neat code. This video is going to be a rant, so honestly, feel free to just not watch it if you don't want to. I got a comment a couple hours ago, and I'm not calling out this person, but they left a comment saying, why is he calling variables pointers? And this is in reference to some like random video I made about this like Silicon Valley clip where they have a linear scan. And I referred to this index as a pointer. A pointer at the beginning, element, sorted list, get the value at the pointer. Does it equal this element? It's a variable. It's an integer. It tracks like the index of an array, I believe, and I called it a pointer. Now, somebody tell me, am I wrong? Like, I really need like somebody to tell me that, because I feel like I'm about to lose my mind. I feel like my head is about to explode. And I got this comment several times on that video. Look, I'm getting confused with you calling pointers to variables. And there's several. Bro calls an index a pointer. How the hell is this a pointer? I got a lot of comments about this. Now, to be completely honest, the main reason I called it that is because in data structures and algorithms, there's many algorithms that use like this term pointer, and they use it differently than technically like the formal definition, which I think the people in the comments were referring to. For example, in languages like C and C++, there is like a technical feature of this language, which is called a pointer. Basically, you have, let's say, your memory or RAM for short. You can have some variable. Let's call it int star, and I'm just going to call it x for whatever. And so this variable will store the location in memory of something, and since it's an integer, it will probably be 4 bytes. And using a pointer, not only can you get the address, like that's what this stores, but if you dereference the pointer, you can get the actual data stored at that location. So that's technically like what a pointer is. I know that. I learned C as my first programming language. Pointer is definitely used in many other contexts in data structures and algorithms. Sometimes it's also used, I think at least, I've heard it used many times to refer to some location on disk. Now, maybe the person who was using that was technically incorrect, because usually it does refer to memory. But I don't think there's anything that wrong, because it still stores an address, not an array. Just in case some people don't know this, when you have an index, the reason index starts at 0 is it's the offset. For example, you have an array. Why does the index start at 0? Because it's saying get the first block. The offset is 0. You're starting to read from the beginning. I concede, technically I used the term incorrectly. I should have just said index. I should have said position. But I like this. If you wanted the first location, you could do this. R plus I, and then dereference that. This is why indexes start at 0. The offset is 0. When it's 1, you get...
Golang has become a favorite in the tech community, and for good reason. It is famous for its simplicity, but in this video you'll see that this is just the tip of the iceberg. There are many other interesting features that make Go perfect for developers who want to build amazing products while enjoying a clean, efficient dev experience. For a bit of context, I'm a developer with 15 years of experience, and my background is mostly in languages like Java, Kotlin, and JavaScript. I experimented with various other languages during this time, but Go is the only one winning me over because it allows me to write better, safer code. On top of that, it forces me to break some of the bad habits I gained in my hardcore OOP and Java days. This brings us to one of the features I believe shapes the way you think about and solve problems in Go, its approach to object-oriented programming. If your background is in one of the many established OOP languages, the first thing you'll notice is the lack of a class keyword. The second thing you'll notice is that the OOP paradigm does not affect the way you write code. This is somewhat liberating, especially if you are coming from Java, where everything revolves around classes, objects, and all the design patterns under the sun. The usefulness of OOP is still debated in the software world. Alan Kay, one of the pioneers of object-oriented programming, has this to say on the topic. I regret the word object. It gets many people to focus on the lesser idea. The real issue is messaging. Messaging is the abstraction of the communication mechanism. It's what allows different parts of a system to interact without knowing anything about each other. That's the power of objects, and it's what makes them so useful. In other words, the real focus of this paradigm is the reliable exchange of information between different parts of a system, and objects are just a means to an end. You'll also find more drastic opinions on the subject, but the usefulness of OOP in modern development is a topic for a different video. Back to Go, we first need to sort out if Go is an object-oriented language. The answer to this question is kind of. Go supports most of the concepts commonly associated with OOP, but it does it in a non-invasive manner. Let's look at some code to better understand what I'm talking about. This is a plain old Java object, which is basically a simple structure allowing you to group together and encapsulate data. Even though you are not familiar with the language, you'll be able to identify a lot of keywords and constructs the developer is forced to work with. You need to use keywords to define the visibility and accessibility of classes, fields, and methods. Then, you need to explicitly define constructors so that you can instantiate your class, and you'll use the special this keyword to refer to the current instance of the class. Things are getting even more verbose when encapsulating your data, since a long list of repetitive getters and setters have to be defined. And, of course, the shit hits the fan if you have to factor in object comparison and equality. In all fairness, JVM-based languages like Kotlin will remove most of this clutter, and projects like Lombok can make Java development a bit more bearable thanks to code generation. However, we can do much better. This is the equivalent of the previous class in Go. We can easily group together data via the struct type, and fields are public when starting with an uppercase letter and private when starting with a lowercase letter. Also, there is no protected field since Go favors composition through embedded typings over inheritance. Polymorphism in Go is achieved through interfaces, which are special types that specify a set of method signatures. Any type that implements those methods will automatically satisfy the interface, so, in practice, interfaces and associated structs can be fully decoupled. It is also worth mentioning that the language designers fought the idea of supporting generics in the language for a long while. One of their main goals is to keep the language simple and easy to understand, especially for those coming from other programming languages. Generics can increase the complexity of the language, making it harder to learn and use efficiently. However, due to community pressure, the idea was revisited and generics are supported in Go starting with March 2022. We discussed OOP principles, so let's now move to something a bit more interesting. While Go is not a functional programming language by design, it does support several functional programming techniques aimed to give you more programming flexibility. Probably the most important aspect here is the first-class function support, which means that functions can be assigned to variables, passed as arguments, and returned from other functions. Go is strongly typed, so you have to use type definitions for function signatures. While this might be a bit overwhelming at first, especially for higher-order functions, it will improve code readability and safety in the long run. Anonymous functions and capturing the enclosing variables surrounding the environment via closures are also supported features, so you should get the picture. Just like Go is kind of object-oriented, it is also kind of functional in a sense that it gives you the right tools for the job without imposing any specific paradigm on you. Don't get used to this though, because Go is not all sunshines and rainbows. You'll see a bit later in the video that some programming behaviors are enforced by the language in an attempt to force you to write more reliable code. One of the most impressive achievements of Go, especially in this day and age, is its built-in concurrency support through Go routines. To better understand this, let's first make sure we are all on the same page and we fully understand the difference between parallel and concurrent programming. In short, you can do concurrent programming on a single core CPU. All operating systems have a scheduler which manages the execution of concurrent tasks. It decides which task runs at any given time, how long it runs, and when it should be paused to allow another task to run. In practice, when you have multiple apps running on a single core, they will run concurrently, with the scheduler giving them access for a few milliseconds. So, on a single core, processes can't run synchronously, but the end-user experience is rarely affected since all threads get their turn to advance their computations in a very short amount of time. On the other hand, parallel programming requires multiple cores with each core executing code at the same time, truly running tasks simultaneously. Under the hood, the Go runtime includes a scheduler that can distribute Go routines across multiple operating system threads, which in turn can be run on multiple CPU cores. This allows your programs to take full advantage of both single and multi-core processors for concurrent execution. Go routines can be paired with channels and the sync package to handle various other concurrent programming scenarios, and this whole topic is deserving of a dedicated video, so please let me know in the comments if you are interested in a concurrency deep dive. I mentioned earlier that Go is not enforcing any programming styles or ideas in your codebase. Well, I lied. One of the most frowned upon language features in Go is its error handling. I'll be honest, this one was hard for me to accept at first since error handling becomes such an integral part of your implementation. Most standard library functions will return two values, one which is the actual result and the second one being any potential error. Then, you have to make the conscious decision to ignore errors, which will make you rethink any corner case scenarios you might be too lazy to care about. So, sure, your functions will not look as compact and clean as they used to in other languages, but the trade-off is really worth it. Before wrapping things up, I have to mention that Go programs compile into single standalone binaries. Everybody mentions how fast the Go compiler is, but the single binary is where I find the most value in. It can be easily distributed and deployed through any type of CI/CD pipeline without worrying about dependencies or environment configuration. Of course, these single binaries come with performance benefits since everything is included, so there is no overhead in loading shared libraries at runtime, and there are security benefits in reducing the number of dependencies and the attack surface. However, at the end of the day, I'm just a lazy developer who doesn't want to waste hours on configuring servers. With Go, you just need to put your binary somewhere in the cloud and simply run your application. I didn't mention features like memory management, control via pointers, or the You either die a hero or live long enough to see yourself become the villain. JavaScript is the most used language in the world for quite some time, and it has definitely turned into a villain for many developers. And let's be honest, the critics make some fair points. As a result, TypeScript has quickly become the go-to language for modern web development in recent years. It successfully addresses some of JavaScript's bad parts, but it does it in a non-intrusive manner. manner, which allows developers to choose how much they want to rely on TS in their projects. This leads to some pretty big differences in TypeScript codebases. For instance, both these snippets are valid TypeScript, but they could easily pass as different programming languages. Due to this permissive nature, things can easily go south when working with TypeScript. So let's look at some of the most important
Hello, everyone. I am so excited today because
You either die a hero or live long enough to see yourself become the villain. JavaScript is the most used language in the world for quite some time, and it has definitely turned into a villain for many developers. And let's be honest, the critics make some fair points. As a result, TypeScript has quickly become the go-to language for modern web development in recent years. It successfully addresses some of JavaScript's bad parts, but it does it in a non-intrusive manner, which allows developers to choose how much they want to rely on TS in their projects. This leads to some pretty big differences in TypeScript codebases. For instance, both these snippets are valid TypeScript, but they could easily pass as different programming languages. Due to this permissive nature, things can easily go south when working with TypeScript. So let's look at some of the most important TS best practices, and we'll break down some of the most common mistakes even experienced developers often make. You'll probably be forced to use TypeScript if you are building for the web, so having a good understanding of the core principles behind this tech is pretty important. Let's start by making sure we are all on the same page and clarify what TypeScript actually is. Your favorite tech streamer will tell you that TypeScript is simply a linter, which, in all fairness, is a good enough definition. However, there is a bit more to the story. JavaScript is a dynamically typed language. In theory, this makes it flexible and easy to use, and its developers enjoy better productivity. In practice, however, all these promises fail when the browser interprets your code at runtime and your logic breaks due to a dumb little type mismatch. This is where the TypeScript static type checking comes into play. It extends the JavaScript language by adding a type system used to define and enforce the expected shapes and behaviors of data throughout your code. This means that you can define the types of variables, function parameters, return values, and object structures up front, allowing the TS compiler to catch type-related errors before your code even runs. Once TS is compiled, usually by some sort of Node.js process, the resulting code is the JavaScript you can load and run in the browser. We can see this in practice with just a couple of easy steps. Let's say you have a basic function that adds up to numbers in a main.js file. In pure JavaScript, there isn't anything stopping you from passing strings or any other type of object as a parameter to this function. To avoid this, we need that extra layer of validation provided by TypeScript. So let's initialize a Node project, install the TypeScript package, and run the tsinit command to set up a project and a TypeScript default configuration file. Now we can rename the previous file to main.ts and add type definitions for our two function parameters. We could even define the type of the return value, but the TS compiler is smart enough to infer that directly. You'll see now that if the add function is called with incorrect parameters, you'll get the appropriate errors in your IDE. Back in the terminal, let's run the tscompile command, and if all the type checks are passing, a JavaScript file with the type stripped is generated. This is what you'll run in your browser. Of course, we can easily define more types and more complex logic, and the same process of type validation, compiling, and outputting JavaScript is followed. Now that we got the basics out of the way, let's look at some rules to follow and mistakes to avoid when working with TypeScript. Quick side note, I just explained the process of compiling TS into JS since this is needed to run your code in the browser. However, there are numerous other runtimes like Deno, Bun, and even Node with the strip types flag that offer first-class TypeScript support. The first rule should be pretty obvious. Avoid using the any type at all costs. I know there will be those corner case scenarios where you don't really know the shape of an object, but for all other situations, you should define and use types. As we already clarified, TypeScript's strong point is the exact type system you would circumvent by using the any keyword. Whenever you are using any, you are weakening the type safety of your program and experiencing unexpected runtime errors, reducing the maintainability of your codebase due to unclear type information, and losing the auto-completion and refactoring support provided by your IDE. As I said, we probably all ran into scenarios when using any seemed like the only option. The API you are consuming might return an unknown value, a third-party library might not have type definitions, or you are forced to work with some JavaScript modules in your TypeScript project. In such scenarios, don't hesitate to use union types and type guards to make your code safer. If you are truly unsure of a variable's type, you could use the unknown type instead of any, or leave out the type reference to allow TypeScript to infer it. The unknown type requires explicit type checks before the variable can be used, which helps reduce the risk of runtime errors. Since I mentioned type inference, remember to avoid overly verbose type annotations when they are unnecessary. So, instead of manually specifying types that can be inferred, allow TS to do its job. TypeScript offers a strict mode compiler option that enforces more rigorous type checking and constraints to enhance code quality and to catch potential issues during development. You can enable this by setting the strict flag to true in the tsconfig file. Strict mode is a combination of several individual type checking options collectively aimed at making your text and syntax likely to be defined. As a result, you should keep things simple. There are a few things to keep in mind. Avoid nested types since they are hard to read and maintain. Avoid complex union and intersection types since they can lead to convoluted and difficult to understand types, and don't overuse mapped and conditional types since they can easily
Nix, a purely functional package manager and system configuration tool that allows developers to say it works on my machine with absolute confidence. It was created in 2003 by Ilko Dolstra, who wrote his PhD thesis on a purely functional software deployment model. 20 years later, it's used by tons of software projects like Mozilla Firefox, Google's IDX, and of course, NixOS, a complete Linux distro based on this package manager. But why Nix? When you set up your own Linux server, the default approach is to SSH into it and start running a bunch of commands that you copied from random places on the internet. The problem is that it quickly becomes impossible to reproduce the state of your machine, and if you mess something up, there's no undo button. Nix users don't have these problems because it provides its own declarative language to define packages, network settings, the file system, environment variables, users, and everything else you need in a .nix file. This file is like a blueprint that can now reproduce the same machine over and over again. Now, any changes to this config are transactional or atomic, meaning everything succeeds or fails together. A huge advantage of that is when you screw something up, you can easily roll back to the previous state. It's like having a time machine for your machine. This is possible because in the Nix store, each package and its dependencies are stored in a separate directory identified by a unique cryptographic hash, which guarantees that packages won't interfere with each other. And with Nix Shell, you can create unique environments for all of your projects. That means side-by-side installation for all of your tools and their different versions without the need for version managers like NVM, Virtual ENV, or Rustup. Because it's all declarative and deterministic, you can organize your configs as flakes and then trade them with your friends like their Pokemon cards. To get started, install the Nix package manager, or better yet, live boot NixOS to try it out as a full Linux distro. Inside the etc directory, you'll find a configuration.nix file. You can think of this file as a function that returns a dictionary or hash map. At the top, we have parameters for config, which gives us access to the entire configuration, and packages, which includes all the packages available on NixOS. Next, with imports, we can break up our config into multiple smaller files to keep things organized. But the real magic of Nix is being able to configure the entire system right here, like set the bootloader to Grub2, or set the time zone to Arizona, or add a user like Alice who has sudo privileges. Not only is that way more efficient than the user add command in Linux, but it's pretty cool. But what's really
All right. Let's go figure out Nix Darwin. So if we go to the homepage for Nix Darwin, there's a lot of stuff about how to install it. We'll come back to this. But what I'm interested in right now is we're creating this flakes setup, and I don't care about any of that because I want to create a minimum viable flake. And here's the reference documentation of all the options is available here. It can also be accessed with man configuration.nix, which is great once you have it installed. Okay, so looking in here, make that slightly bigger. What am I looking at? Configuration options. Documentation.enable, whether to install documentations of packages from environment.system packages into the generated system path. That's probably a good idea. There's a lot of stuff in here. It's probably a good idea. We're going to skip most of it though, but I'm showing you that this page, or that man page, which is exactly the same material, it explains a lot of what you can do, and this is how you figure that kind of thing out. So one thing I want to do is I'm going to search in this page for programs.zsh. Okay, so whether to configure the ZSH as an interactive shell. So I want to actually set up ZSH as my shell in the system. I'm going to install it for all users, which means I'm going to do it here under in the Nix Darwin module. Okay, so programs.zsh.enable equals true. That's going to automatically install it for me. Now I could have just had it installed. In this case, when you do it like this, it creates some default configs, and we can add more things to add, like have specific configurations, which we're not going to do right now. And then I'm going to say environment.shells equals packages.bash and packages.zsh. Oops. Cool. So that was in here under environment.shells. it's a list of things, sure. All right, next, let's
So here is a short lecture that unfortunately you have to learn for the exam, maybe for one question. It is a way to do migrations to Aurora MySQL. So if you have an RDS database and you want to move it into Aurora MySQL, the option number one is to take a database snapshot from the RDS MySQL database, and you restore this snapshot as a MySQL Aurora database. Potentially, you'll have some downtime because you have to stop operations on the first MySQL database before migrating to Aurora. The option number two, which is more continuous, is to use and create an Amazon Aurora read replica on top of your RDS MySQL. So it's a possibility indeed. And once the replica lag is zero, that means that once the Aurora replica has fully caught up with MySQL, you can promote it into its own database cluster. Now, this can take a bit more time than the database snapshot option and cost some money because of the network cost that may be associated with this replication. The other option is if you have a MySQL database that is external to RDS, then you can back it up using the Percona backup extra backup utility. This will create a backup file and you put it in Amazon S3. And then there's an option from Amazon Aurora to directly import this backup file into a new Aurora MySQL DB cluster. Just so you know, this only supports the Percona extra backup utility. The other option is to use the MySQL dump utility to run it against a MySQL database, and you would pipe the output of this into your existing Amazon Aurora database. So this is taking a lot of time, and this does not leverage Amazon S3. And a last option is to use Amazon DMS if both databases are up and running to do continuous replication between the two databases. We do the same process for PostgreSQL. So for RDS, it's pretty much similar. You have two options to use the database snapshots restored as an Amazon Aurora database, or you create an Amazon Aurora read replica of PostgreSQL to have a read replica, and then you wait until the replication lag is 0 to promote it into its own database cluster. And if it's an external external PostgreSQL database that you want to migrate to Aurora. You can create a backup of it, and then you put the backup in Amazon S3, and then you import the data using the AWS S3 Aurora extension, and this will create a new database out of it. And finally, again, you can use DMS to migrate from PostgreSQL to Amazon Aurora continuously. Okay, that's it for this lecture. I hope you liked it, and I will see you in the next lecture. Okay, so yet another theoretical lecture, but I still want to mention it because I think it's extremely important going to the exam. You need to know about the services that AWS offers at a very, very high level, but just hear one about them once to do on-premise strategy with the cloud. So we have the ability to download the Amazon Linux 2 AMI as a virtual machine, and that will be in the ISO format. And you can load this ISO image into the common software used to create VMs. So that includes VMware, KVM, VirtualBox, which is Oracle VM, or Microsoft Hyper-V. And this would allow you to run Amazon Linux 2 on your on-premise infrastructure directly using that VM. So that means that you can make it work with some user data and so on. So quite cool to think about. Then we have a feature called VM import and export. And what this allows you to do is to migrate your existing VMs and applications into EC2 directly using this feature. And you can also create for example, a disaster recovery repository strategy if you had a lot of on-premise VMs, but you wanted to back them up into the cloud. And because it's called import and export, you can export back the VMs from EC2 to your on-premise environment if you wanted to. Now, for AWS Application Discovery Service, well, this is a service that allows you to gather information about your on-premise servers and plan a migration. This is very high level, but it does give you some server utilization information and dependency mappings, and that could be quite helpful when you want to do a massive migration from on-premise to the cloud. Finally, you can track all that migration using the AWS Migration Hub. Then we have AWS Database Migration. service, or DMS, which allows you to replicate from on-premise to AWS, AWS to AWS, or AWS to on-premise for your database. So this is quite nice because if you had a MySQL or a Postgres database running on-premise and you wanted to start moving your workload into AWS, you could use DMS to replicate the database in the meantime, and when you're ready, you can fully transition to using AWS only. And the nice thing about it is that it works with various database technologies. That includes Oracle, MySQL, MySQL, DynamoDB, etc., and allows you to do some really kind of fancy use cases. For example, migrate data from MySQL into DynamoDB. Okay. And then finally, we have AWS Server Migration Service, or SMS. And this is for incremental replication of on-premise live servers to AWS. So you can replicate the volumes directly into AWS. And this is used for more ongoing type of replication. Okay, incremental replication. And this is the last one that I have in my mind for on-premise migration to AWS. So at a high level, you may be like, oh, this is a lot of services. Just remember the names at a high level. So Linux 2 on-premise is possible. We can do VM import and export for on-premise and EC2. We can have migration services such as Application Discovery Service, AWS Migration Hub, Database Migration Service, and Server Migration Service, DMS and SMS. And just remember those at a high level. That's it. Just so you can see, if you see the name in the question, then you're not taken by surprise, okay? You know that all these things have to relate to on-premise, okay? Well, that's it for this short theory lecture. I will see you in the next lecture. Hello, and welcome to this